I'm really nervous right now because I'm going to talk to you about the self-assembly patterns of Diblock copolymers with high levels of molecular repulsion. Now, so move to the left. Okay. So now, what are Diblock copolymers? I have Tic Tacs in my mouth. So how many of you guys have sneakers, drive a bike, drive a car, take medication, or have a computer? Any of you? How many of you have a computer? That's a lot of you who have a computer. Wow. Okay, so then in some small way, probably, you've all been affected by the wonderful innovations of copolymers. Now, copolymers are these molecular chains that have the interesting property of being able to self-assemble into these small synthetic structures that that have several wonderful, unique properties, and so they have been used in for innovation in fields such as computer hardware, pharmaceuticals, photovoltaics, thermoplastic synthetic rubbers, and well, sneakers are also rubbers, different type of rubber. And so they actually have a wide variety of applications in several fields, and so I thought it would be interesting to talk about them. So what are they exactly? Well, so you have there a diagram of some chains of molecules. You have like an A and a B chain. So each of those chains are made up of these small molecular monomers. We call them blocks. There's two different types, A and B. And so when you actually have them in long chains and you covalently bond them together, you have this long macromolecular chain called the Diblock copolymer. Now, due to like the chemistry, for lack of a better term, of each of the types of blocks and how they interact, they acquire a unique amphiphilic behavior together that allows them to aggregate with similar copolymers. And actually, in high enough concentrations, they're actually able to form these cool synthetic structures. Now, this is like a layered structure. There's actually several other types of structures that can form based on two variables, F and chi. And so F is one variable that F is one parameter that we look at copolymers. F represents like a volume fraction of a copolymer. So like for a single chain, Fa refers to how much of this chain is made up of this A type of polymer, A type of block, and Fb refers to how much of this chain is made up of this B type of block. And so depending on those values, we can actually form, as you can see, several different types of structures. This is like a layered structure. This is called a gyroid structure. It's like an interlocking cave thing. This is a cylindrical structure, and these are spherical structures. Now, as you can see, with different levels of F values, these structures are more likely to form. I have some values here, but I'm not really going to list them out because these are more approximate values, and because we have a second variable that we need to take into account when we're looking at what structures are more likely to form, which I'm going to focus more on. This variable, this parameter, is called chi, the Flory-Huggins interaction parameter. And so here's this beautiful equation right here, which is so very easy to understand. It requires like college-level understanding of thermodynamics and chemistry. So this equation is a generalized formula for the flow of free energy, delta Gm, in a polymer mixing system. It takes into account several things: temperature, flow of free energy, entropy, and several other factors. The two researchers that Flory and Huggins, who created this equation, also introduced this parameter chi, and this variable represents a theoretical energetic cost or energetic difference value. So if I have a chain made up of A and B blocks, the difference in like their innate energy, so like internal energy, thermal energy, potential thermal energy, can be kind of represented with this variable chi. And so with higher chi values, then there's like a greater difference in energy between the two types of a chain, between the two blocks in a chain. And so obviously chi depends on which two types of block A and B I have. And so different combinations of A blocks and B blocks, different A and B blocks have different values of chi, and so they interact differently. So let me go to the next slide first. Let me show you this diagram. If you see here, this is not really a graph. It's more of like a two-variable matrix. On this horizontal axis, we have F values, which represent, I told you that already. And on this vertical axis, we have chi values ranging from 0 to about 80. Now, in this graph, we stop looking at this value of 80, and we don't really look at higher values of chi. And so the reason for that is because copolymers with higher chi values then tend to have like higher levels of unstable energy interactions. As we can see in the equation, an increase in chi leads to generally an increase in like free energy flow. And so with greater free energy flow, This results in systems that are not quite as stable, and so they can't really, I'm trying, I have to talk this fast. And so they're generally not as stable as they would necessarily need to be in order to form these synthetic structures. So many believe that at higher levels of Chi, you actually can't have any of these cool structures. So some researchers don't even try to look. But what's the deal with this number 80? I don't like 80. Why didn't they stop at 100 or 200? For whatever reason, also this diagram is adapted from two researchers, Mattson and Bates, who are actually have numerous contributions to the field of Diblock copolymers. But why did they stop at 80? Why not at 100? Which is what I'm trying to look in more. What's the furthest I can take this thing? So the list of unique, useful copolymers is not as long as we'd like. As you saw before in like that first slide, there are several amazing applications for these copolymers. But those ones I showed with like shoes and computers, those are really like the best ones we have. There's not many more we'd like to make. There's many more we'd like to make, but there's not many that we believe even that we can make. And you know, research labs have exhausted the possibilities available in this narrowly defined range. Like, you can't do anything about the F value, but like for Chi values, if you try like working on the theory of and inspecting higher Chi values, then maybe you can open up the range and look at even more types of molecules with higher types of Chi values. So what I'm trying to do is break this upper limit, and you know, there's a fun animation just for some cheap laughs. I'm trying to go past this upper limit and see if I can actually, if higher Chi values are actually able of, copolymers with higher Chi values are actually capable of sustaining these physical 3D structures. So, and this is to increase our list of likely viable copolymers, because if I can prove, or if we can prove, or at least show that copolymers with higher Chi values can form, then more researchers will get on it, and they'll actually start inspecting and doing research and doing trial applications for more materials with these copolymers with high values of Chi. So how I went about this is, well, my mentor devised an original algorithm for this that allowed for simulations of the conditions necessary for a copolymer phase structure to form. It regulated temperature, it regulated like energy flow. It was too complicated for me to understand. So there are, it also allowed for me to input variable parameters, df and chi, that I discussed earlier, to be input for a theoretical Diblock copolymer. The ranges for the values are, there's a typo, 0.05 to 0.36 for F and 100 to 400 for Chi. And so it also allowed for you to like pre-shape the copolymer structure. Like I showed you those 4 different types of structures before. The algorithm actually allowed you to start the copolymers off in a certain type of shape, and that was really just for simplicity and also to because it better stimulates. It was better to easier track if something was going to be more stable or not. And so the program was run through the Stampede supercomputer at the Texas Advanced Computing Center. So this was a really high-level program that required an amazing amount of computing power, and it required 256 computers working in parallel to work on them for 48 hours each for each trial run. And each time it cost a significant number of grant money. So I could only really inspect 6 trials. And so I might not have something incredibly conclusive. But for those 6 trials I ran, the program returned raw data sets of the simulated copolymer melt, the algorithm did at least. And so from those raw data sets, we could actually visualize them with ParaView and MATLAB. ParaView let me visualize the actual data sets in like a 3D form, which was very nice, and I'll show you some of those in a second. And MATLAB actually recorded data. It like inspected the data sets and like tracked trends and such. And so here are some of the tested cases. Let me go to the next slide first. So here we have actually a diagram of one of the copolymers. If you see this red area, that's a concentration of like an A type of block. I'll just arbitrarily call it A. And if you see these blue areas, this is where you see concentrations of a B type of block. Actually, there's more blue areas, but for the simplicity of, for visibility, I use ParaView to like omit some of it out. And so this is like a spherical structure in the center, and these 8 edge things or 8 corner things are also part of a spherical structure. So what's interesting is here's the range of values. I made sort of formatting here, but these Chi values are ranging all the way from 100 to 400 I chose. And so in these few frames, the test cases I checked actually showed sort of a stabilization of the adopted spherical shape in all cases. And through several frames of progression through time, the the A blocks in the red color actually became more concentrated and solidified their spherical structure, which seems very promising because I thought, okay, wow, then actually higher chi values actually can sustain these spherical structures. However, upon talking to my mentor for like a second, I was notified that since there are limitations in both the algorithm and pair view, it's unclear if this is an absolute stable state or a local stable state. Now, the algorithm can only track the state of this so far, and so we're not entirely sure how actually reliable or conclusive that data is. But at the very least, while this data is not conclusive enough to validate scientific trials of copolymers with high chi values, at the very least, it should open up like at least more of a discussion or at least more research into this field because there is really a wide variety of copolymers we can look at. And so I'm kind of rushing for time. I'm not even sure what I'm saying right now. Personal gain. I added this slide because I thought I would have time. I evidently do not. College is tough. Research is tough. Entering a new field of science is tough. I had to read so many papers on this. I don't know what I meant by this fourth line. I'm not revolutionizing anything. I didn't find anything. Humanity's extensive knowledge and capabilities so far is unbelievable. The work that college people do and professors and graduate students is unbelievable. So here's my quick acknowledgement section. That photo was taken from Facebook. That was the only photo I could find. That's the back of my mentor's head that I took from. I'd like to acknowledge my mentor, my mentor Gaddy, my research partner Jillian, who's up next, and she'll do a better job than I did. Director Lena Kim, right there, who's rushing me. Ross Meltzer, Michael Knipp, and my parents who are somewhere in here, actually, I think. So, yeah.